Today we'll begin our discussion of periodic trends. As you can see on the screen, there are four main trends, and I'm going to go through each of these trends, define them, and then hopefully explain how they occur. Let's talk about this minor trend first. This is metallic character. As you can see from the arrows at the very top of the page, the best metals on the periodic table are found on the left-hand side. Likewise, the best metals are found toward the bottom of the periodic table. And there are reasons for that. The primary reason is that a metal is defined as an element that easily loses its electrons. And it's really that and not malleable and ductile and conductors and all those things, but really it's the chemical property of losing electrons. If we really want to give a gold medal, if you will, for the best metal, it would go to francium or cesium because they are in that bottom left-hand corner. The reason francium and cesium lose their electrons so easily is because they have a low ionization energy. And that ionization energy arises from the atom's radius and as well as the attraction the electrons have for the nucleus. To understand the periodic trends, we first have to have a good grasp of these three definitions. The first one might be the most important. It's Coulomb's law. Coulomb's law is a physics term that we're going to use in chemistry here. We're not going to be calculating the force, the actual force between electrons and the nucleus, but we're just going to use the Coulomb's law to help explain why some electrons are more attracted than others. But as you can read from the definition, the Coulomb's law is a basic law of physics that tells us the force between charged particles. It depends on the charge and the distance, and that becomes very important between the two charges. The next term is shielding. You should know now that electrons repel each other. The electron cloud is nothing but electrons swimming around, and they're all repelling each other. The valence electrons on the outside are going to be repulsed by the inner core electrons that are between them and the nucleus. And that effect of pushing away the valence is called shielding. And finally, we have effective nuclear charge. The effective nuclear charge is that piece, that fraction of the total nuclear charge that the valence electrons actually get to see. It's because the nucleus and that total positive charge is shielded from the valence electrons by those inner core electrons. So way out on the back end, the valence electrons don't get to experience what, say, the 1s electrons are experiencing. There's a real short equation to calculate the effective nuclear charge. You can see it at the bottom of the screen. It's the number of protons minus the number of inner core electrons. I'll go ahead and spoil the surprise for you. The effective nuclear charge ends up being the same as the column number for the main group elements. Now, just a little more about Coulomb's law. You can see the equation written or seen on your screen here. It's kind of complex looking, but I want to ease your fears a little bit. First of all, F is the force of the attraction that we're talking about. And then we have a lot of different letters. Next is K. K is the Coulomb's constant. We're not going to use that at all. It's just there to show the proportionality between F and the other variables. So we're just going to kind of leave that one alone for now. The ones that we do care about are going to be the Q's, and notice there's two of them because the force of attraction always has to be between two different things. The electron, the Q stands for charge, and the electron has a charge of -1. Really the important thing here is that the force is proportional to Q, and that is a direct proportion. If the value of Q goes up, in other words a +2, then the force is going to double. If you go to +3, the force will triple. They are directly proportional. Then we have the one that really makes a significant difference, D. D is the distance between the nucleus and that valence electron, or between any 2-point charges. Now this proportionality is somewhat more complex. It is not a direct proportion. It's not even an inverse proportion. It is an inverse squared proportion. That means that if D goes up, the force is going to decrease and decrease quickly. For example, if I double D, that means it's going to cause the force to go down by 1/4. They are inverse operations. All right, let's practice a little bit. I kind of went through this one already, but just to be probably more clear about this, how would the force change if the value of the charge on the nucleus doubles? Well, we know that the force is proportional to Q. So if I double Q, then according to algebra, I have to do the same thing. This is a direct proportion. I have to double the force on F. So it's going to double. In the second bullet, how would the force change if the distance between the nucleus and the valence electrons doubled? Well, this time, remember, we have the force is proportional to 1/d squared. So if I take that, and I have now 1/2d squared, I'm doubling it. This is the same as 1/4. It's 1/4d. So to keep this proportionality intact, I'm going to have to do the same thing to this side, which means that's 1/4 of the force, or the force is fourthed. The first actual trend that we want to dig into and describe using our 3 new terms, Coulomb's law, shielding, and effective nuclear force, is atomic radius, or size of the atom. Very clear here that the atomic radius, the size of the atom, increases as you go down a column, and it decreases as you go left to right across a row. The biggest atom that is not radioactive is cesium. Francium would get this award if it weren't radioactive. So as you go from alkaline metals to alkaline earth metals, that's smaller, to the group 3 elements, smaller, carbon group is smaller, nitrogen group smaller, and the noble gases are the smallest. And then toward the bottom of every group, you're going to have the biggest element in that group. Well, the question now is why? Why does it happen this way? So here are the big questions in regards to atomic radius. Number one, why does the atomic radius increase as you go down a column? That question isn't as complex as you might think. It's a very simple answer, in my opinion. As you go down, you're increasing the number of shells, of energy levels. And there are more electrons on each energy level. And they're all repelling each other. So that causes the thing to swell out. More layers to an onion means a bigger onion. So very simply put, the reason you get bigger as you go down is that there are more energy levels. Then a little harder question is, why does the atomic radius decrease as you go left to right across the row? This is going to have very little to do with how many energy levels you have. This is going to have more to do with the charge on the nucleus and the amount of shielding that the valence electrons have to go through to quote-unquote see the nucleus. As you go from left to right across the row, the effective nuclear charge is going to increase. Very simple the atomic number is increasing. You're adding protons to the nucleus as you go across a row. So it's getting more positive. Well, at the same time, the inner core of every element is going to stay the same on that row. The shielding is fairly constant. Everybody on a row, every atom on a row has the same amount of shielding. The result of all that is that the valence electrons, as you go toward the right-hand side of the periodic table, are going to see a greater effective nuclear charge, more protons, same shielding, same energy level they're all on, and thus, according to Coulomb's law, you'll have a higher force and everything will be closer together. So there's the explanation kind of typed out. Just hit pause and take a moment to read that and see if it sinks in. Real quickly, here's just a brief graphical illustration of what I was trying to explain about the inner core being the same for two elements on the same row. Here are lithium and beryllium. Lithium's on the left, beryllium's on the right. They are on the same row, row 2 of the periodic table. Both of these atoms have the same inner core. Let me circle it for you. Their inner core will both be 1s2. Now, the major difference between the two, obviously, is that lithium has 3 protons, beryllium has 4. For each of them, the valence electron, and of course, beryllium has 2, but we're only looking at one at a time, is about the same distance from the nucleus in each atom. So you have the same distance, the same inner core, so the same interference, the same shielding for both of those valence electrons, but beryllium has one more proton to peer through the cloud. So beryllium, the valence electrons of beryllium will see more of a charge, more of a force from the nucleus, and be held tighter and closer together.